All righty. So with that, I guess I'm going to turn over to the MC for the posters and the 2-minute lightning talks. So with that, let's welcome co-organizer Yusuf Naderi.
You want to mention the awards and the award voting thing that?
Yes. Okay. Yes. We hope you enjoy the latest updates from our sponsors, Masswork, National Instrument, ETAS Media, Tech, and Analog Devices that are really investors in the research and development of the software-defined community and empowering this community. By that, we'll start the pitch. We have 3 awards this year. Please have the voting ballot from the front desk. So we give one award to the poster, the best posters based on your votes, one to the best pitch, elevator pitch, and one, if you put your name, you will also go to the winning gift card just by participating in the voting process. Okay, so we can start with the first pitch. Please use 2 minutes and briefly describe your presentation. Adversary UAV localization with software-defined radio. Please welcome Ian Gilman from WPI. So you have 2 minutes.
Yep. Thank you very much, Michael Youssef. So came here to present on my senior design capstone project, Adversary UAV Localization with Software-Defined Radio. The 2-minute gist of the project is that I actually just today learned about, I believe it was SigSafe was the company that was actually doing a similar project on boats, right? As it would appear. So essentially, the project is in that similar vein, but what we're doing is we're using 5 EDIS USRP2 radios to perform RSS calculations in the band of the actual transmit frequency of the DJI drone, the DJI UAV's transmission waveform. So essentially in the 5 each radio, we get an RSS measurement. From there, we can then, we use a one-dimensional mapping function which maps RSS to a one-dimensional position. Once we have an array of one-dimensional positions, we can then move into a Python web server, which then performs an adaptive filtering algorithm called recursive least squares, which then gives a 3-dimensional coordinate for the actual drone. Moving then forward, it's then displayed on a graphical user interface for the user. We compared our ground truth in experimentation of actually putting the drone in a known 3-dimensional location and then recording the actual transmitted waveform from the drone back to each radio. And then from there, we then compared it again, our position fixes against the Kramer-Rao lower bound for unbiased estimators for the same scenario. And we found that we approached the Kramer-Rao lower bound did not exceed, and we were able to get within standard deviation of error for what the Kramer-Rao expected us to get. So I'll actually have the poster on a laptop outside, so we can discuss about that presentation later. So thank you very much for the time.
Great. Thanks, Ian. The second poster pitch deck here is comparison of coherent and non-coherent receivers for IEEE 802.15.4 OQ-PSK modulation based on SDR platforms. Please welcome Ivan Faulkner from UConn.
Hi, everyone. As he said, my name is Evan Faulkner. I'm an undergraduate student at the University of Connecticut, and I'll talk a little bit about this mouthful of a project title. I have too many slides here, but I'm just going to give you the quick rundown of what's going on in my poster over there. So the idea of this project is that I've taken the IEEE 802.15.4 OQPSK physical layer specification and developed the standard receiver for the physical layer and a new coherent receiver and compared their performances. The OQPSK physical layer is designed in such a way that it can be decoded by a non-coherent decoder, which is very simple to implement, relatively robust, and depends on a sort of duality between OQPSK and MSK so that the waveform can be decoded as a frequency shift keying waveform instead of the phase shift keying waveform. The next thing that I did after evaluating this MSK non-coherent receiver was implement a coherent receiver, which involves equalization, timing synchronization, and then just coherent decoding of that waveform. And I found that we can, by implementing this slightly more complicated coherent decoder and receiver, see a pretty significant improvement in the performance of decoding. So I have some curves on my poster over there that you can take a closer look at, but our preliminary results show improvements in up to 6 dB for the packet delivery ratio to SNR curves. So that says, more than doubling the distance, quadrupling the coverage for the same transmitter, the same power transmitter, just by implementing this new, slightly more complicated receiver. So if you have any questions about that, come talk to me. If you're interested in a GNU radio implementation of this, if you're interested in Zigbee, then we could talk about this, and that's sort of the next step with my research here. So thanks for your time. I hope to talk to some of you in a minute.
Good. The next pitch, scientific measurement of near-Earth space, effective RF data strategies using software-defined radio architectures. John Soboda from MIT. Yes. Okay. So here. Oh, yeah. Okay. HTML?
Yeah, HTML. Okay.
Are you ready? Oh, okay. Yeah, but we only have VGA.
No, that's fine. I'll just talk to it.
Okay.
So hi, I'm John. I'm a geospatial research scientist from MIT Haystack Observatory. We're in a little bit. We have slightly different requirements than a lot of you. We don't have as many real-time requirements because we are a radio observatory. Our main model of work is to collect RF level data and keep it for later analysis. So we've developed our own API and data standard called Digital RF. What that allows you to do is to save your RF data in an open and easy to use format, along with another format for the metadata we call digital metadata. And what that does is it ties your RF and your metadata together in a nice set to archive your data and be able to go back and either reprocess or rerun your simulations. And so it has a really nice package. We have wrappers for it in both Python and MATLAB to do data reading. We have a number of different types of recording software in Python and C++. And we've used it extensively at the Haystack facility, and especially at the Millstone Hill radar that we run, where we're actually using digital RF as the main data container for the radar system. So feel free to stop and talk with me at my poster or just during one of the social hours here.
Great. The next pitch, Visible Light Communication System and Open Source GNU Radio Toolkit, Jason Nian from University of Massachusetts, Boston.
Hello everyone, my name is Jason Nguyen and I just graduated like last May. So my senior design, we create a visible light communication via testbed so that we can transfer data through LED as the light you see up here. For example, you hold the phone like this and you will have internet connection. So my project related to like physical layer networking and signal processing. And for the physical layer, I use USRP, the X310 for receiving and transmitting data for like, let me think, sorry. So at the transmitting data, I use like the GMSK modulation and from GNU radio and transfer the data to the USRP, and the signal will go through the light, and the light will transfer to a photo sensor where it will be decode and sorry, the data will be decoded and reconstruct back to the original data. And we, for the result, we have like a test bed, and we try to connect to the internet connection, and we already connect to basic website without pictures, only text website. We will work more on like increasing the speed of the test bed, as well as like expand more like multiple cells instead of like only one LED and one receiver. So that's it for my presentation. Thank you.
We go to the next, development of a protocol to access white spaces compliant GNU radio block. Hector Reyes.
Good morning. My name is Hector. I am from Colombia. I work at a university in a town called Villavicencio. I am going to present the development of a GNU radio block that communicates with TV white space databases. The objective is to provide a block for developing TV white space radios with GNU radio. This is part of a bigger project that we are doing at the university. We are developing a TV white space radio with GNU radio. So white space, as you know, is an unused channel. And in the TV white space specifically, we are talking about TV digital channels that are not used in the region. So the way it can be accessed is through a database which stores all the information related with the channels, the schedules, the maximum power allowed for the radios to use. And this protocol is called the POS protocol to access white spaces, which has been specified by the IETF through the RFCs 7545 and 60. I think it's the 6953, is a standard for the radios to comply with. So what we did was it was a block that communicates to the internet to get the information. And the protocol defines very specific messages to request and to respond. Everything is done through to a master device which communicates directly with the TV-wide database server and can give the information about available spectrum to other devices called the TV-wide space slave devices. This is an example of a transaction where the TV-wide space master device is requesting information about available spectrum to the database, and the database is answering back. And here we have the log integrated into a very simple GNU radio flow graph. The objective of doing this way, and not because I could have done it using Python and not in the GRC, but the objective is to be more academic, to show the students how this block connects with the databases and gets the parameters for the operation of the radio. The future work includes for this block to control all the operation of the radio, and to even negotiate with the TV-wide space databases for spectrum, which you know is the future of spectrum sharing. Thanks.
Great. So go to the next, tracking anonymized Bluetooth devices with Johannes Becker from Boston University.
Hi, my name is Johannes Becker. I'm a PhD student at BU with Professor Starobinski. I'm going to present a paper. A poster is not up yet. It's going to be up in a minute. Thank you. Based on some work we did last year, and that will be presented at the Privacy Enhancing Technology Symposium in July. Basically, Bluetooth allows, since the Bluetooth LE standard, Bluetooth allows devices to use pseudonymous, randomized addresses that change over time to protect against device tracking. And we use a HackerF to listen to Bluetooth advertisement communication. Basically, Bluetooth advertising is just broadcasts that devices put out in regular intervals, pretty frequently in many cases. And we just passively listen to that traffic, and we found a way to track these devices beyond the point at which they randomize their addresses. So this is just, in a nutshell, all the details and some examples and results are on the poster, and come see me for more details on this. Yeah, thanks.
Next, wireless attacks on aircraft instrument landing systems. Harshad Sasi from Northeastern University.
So, hi, I'm Harshad, and I'm going to present a poster today about wireless attacks on aircraft instrument landing systems. So, as you know, ILS is a key landing system or a radio navigation aid used by aircrafts all over the world for safe approaches in poor visibility conditions. So it has like three main components. You have a localizer, which provides horizontal guidance, a glide slope, which provides vertical guidance, and marker beacons, which acts like a checkpoints over your approach. So our work is about figuring out systematic attacks or wireless attacks on the system, so that you can manipulate the instruments and misguide the pilot while approaching the airport. So we have like a quick proof of concept video. All right. So basically, that was like a proof of concept which we developed. So since we cannot try it on real aircrafts, we used FAA accredited simulator, and we also generated like live signals using USRPs. And of course, everything was in a wired environment so that there was no signal leakage. And to put things into perspective, this is like the evaluation that we did. So if you spoof offsets, you can make an aircraft land 100 meters away from where it's supposed to, laterally, which if you see, it makes the aircraft land probably on a parallel taxiway or in fact on a parallel runway, which there probably some other aircraft taking off or landing. And if you spoof the glide slope, you can make the aircraft land a kilometer before it is supposed to land. And if you see Boston's runway 4, or rather any runway, you'll basically land in water. So, well, that's my work, and my poster is the third one from there. So to know more, feel free to we can chat on this and in the poster session. Thank you.
Great, thank you. So the next speech is Cosmos Testbed Introduction, Michael Sherman, Rutgers University.
Okay. Hi, I'm Mike Sherman from WinLab at Rutgers University. I'm here to talk about the Cosmos sort of radio testbed we're building in New York City. I've also got too many slides, so I'm going to try and rush through these. The goal of what we're doing is to try to build a realistic RF testbed outdoors in New York City with a focus on very wide bandwidths, very low latencies, and having lots of very fast and very close edge computing. To that end, we're building this out over about a square mile of West Harlem between Columbia University and City College. We've got roof-mounted fixed radios, wall-mounted, lamppost-mounted. We have a number of portable SDRs, both sort of person-carried and vehicle-mounted, to try to get sort of interesting the travel patterns and content types. For the fixed radios, each of these sectors, we've got a mix of single sector and multi-sector installations. Each one is off-the-shelf SDRs from National Instruments, specifically the N310 2974 and the E312 for mobile. We've got a limited millimeter wave deployment we're rolling out, some off the shelf and some is a collaboration between Columbia University and IBM. Everything is tied together by optical backhaul to some circuit switches, so you can build arbitrary topologies as the backhaul. That's all connected to a big pile of compute, CPU, GPU, FPGA. It's hooked up to 10, 25, and 100 gigabit networking. And this optical backhaul, and it's also hooked up to a bunch of public clouds. So anyway, I look forward to hosting your experiments, and please contact me with any questions.
Thank you. And the last speech is a localization with Palo SDR, William Schwartz.
Hello, my name is William Schwartz. Lauren Getz and I made an indoor localization system for IoT spectrum monitoring. We used the analog devices Pluto. Our goal of the project was to localize sub 1 gigahertz waves, so we focused more on the low end of the 6-LoWPAN standard. We specifically looked at the Z-Wave standard. And so we localized within the 908 megahertz band. sorry, I was a little bit unprepared. I'm sorry, I'm lost.
So what did it do? Like what did you ultimately do with the testbed? How did you localize stuff?
All right. So we set up the Plutos to wirelessly communicate with one another. So the Plutos already support drivers for wireless cards. So we networked all the Plutos together wirelessly, and then they would then wirelessly localize sub-1 gigahertz signals. So they would communicate on 2.4 gigahertz via Wi-Fi network. And then we had a web interface and a server, so we would constantly display the current localization estimates of our transmitter device throughout the hallway that we were localizing in. Thank you.
Please support the posters and presenter with voting. The voting sheet is in the front desk. This Mike.
All right, so that wraps up our morning session for things. We're a little bit early on this, so we're going to extend our network time, and that's actually one of our favorite things about NEWSDR as a workshop, is the ability to spend time together, network, communicate with our peers across industry, academia, government, and so on. So over the next 45 minutes, we hope you take the time to walk around, see some of the posters that are presented up here. Also, in terms of our sponsors that are out by the registration table, spend some time out there looking at some of the excellent demos that they have that they described a little bit at the beginning of the day today. And also, if you partake, a little more coffee is always available to keep us running and going for the day. Besides that, we will get back together around 11 o'clock back in here to start our next presentation, which is our first technical talk of the day. And looking forward to keeping that going and rolling along. So thank you very much, and enjoy the little break in session here.